Annapolis, Maryland, May 1945. Dr. Robert Goddard stood still inside the Navy Labs warehouse. He just stared at the thing in front of him. He wasn't doing so well at the time, and throat cancer had made his voice a raspy whisper. He reached out and touched the cold metal side of a German V-2 rocket. For 20 years, he had been the only one in the United States who really believed in rockets. He built liquid-fueled rockets with very little money. The government didn't pay attention to him, even when he asked for help. Now, in this dimly lit warehouse, surrounded by Army officers and Navy engineers, Goddard realized something important that would bother American rocket science for the next 10 years. The Germans didn't just make a rocket. They had completely changed how rockets were made. America had missed out. As Goddard walked around the 46-foot-tall missile, he didn't know that what he was seeing showed how far behind the U.S. was in technology. American scientists would spend the next 15 years trying to catch up. The V-2 wasn't just better than what America could do. It used technologies that America didn't have. It had ways to solve problems that American scientists hadn't even thought about. It was made with a level of precision that American factories couldn't match. The rocket in that warehouse proved that while America had Robert Goddard, Germany had Peenemünde. That place was a huge research center with thousands of scientists, lots of money, and a 7-year head start on making rocket technology into weapons. This technology would change how wars were fought and how space was explored. The story of how America found out it was behind in rocket technology starts not in 1945, but in April. American forces were moving quickly across Germany, and they came across something that would change the course of history. April 11, 1945. The Harz Mountains, Germany. Soldiers from the U.S. 3rd Armored Division went into the Mittelwerk underground factory near Nordhausen. They thought they would find another German weapons factory. Instead, they found a huge industrial operation. Tunnels went deep into the mountains for miles. Production lines had partially built V-2 rockets in different stages of completion. Warehouses were full of parts. Rooms had stacks of technical documents. Everywhere you looked, there was proof of forced labor, skinny prisoners from the Mittelbau-Dora concentration camp. Some were barely alive. They had been forced to build Hitler's revenge weapons. Major James Hamel of the Army walked through those tunnels, and he couldn't believe what he was seeing. The Germans had been making 600 V-2 missiles every month. Each rocket needed 50,000 parts. The precise way they were made, the quality control, the logistics of moving parts through those underground production lines. It was an industrial achievement that seemed impossible, especially for a country that was supposedly about to lose the war. But Hamel understood something the infantry soldiers didn't. These weren't just weapons. They were the key to the future. The Soviet Union was going to take control of the area in a few weeks. Everything in this factory, every document, every part, every rocket, would go to Stalin unless the Americans acted fast. Within hours, Colonel Holger Toftoy got orders from Washington. Get the rockets. Get the documents. Get them out before the Soviets get there. What followed was called Special Mission V-2. It was one of the most important intelligence operations of the final days of the war. American troops worked day and night loading railway cars. They filled 341 cars with V-2 parts, enough to build about 100 complete rockets. They also loaded tons of technical documents. All of it was being rushed to the port of Antwerp. There, ships were waiting to take America's prize across the Atlantic. By late May, the first parts arrived at the White Sands Proving Ground in New Mexico's Tularosa Basin. Army engineers started making a list of what they had captured. With every crate they opened, with every technical drawing they looked at, it became clearer how much the Germans had achieved, and it was disturbing. The V-2 rocket, called Aggregate 4 by the Germans, was 46 feet tall and weighed almost 28,000 pounds when it launched. It could carry a 1-ton warhead 200 miles with decent accuracy. But these numbers didn't tell the whole story. The real surprise came when American engineers started taking the rocket apart to see how it worked. The engine was at the bottom. It was a huge combustion chamber that could produce 60,000 pounds of thrust. American engineers who knew about Goddard's work were amazed. Goddard's biggest rocket engine had made 985 pounds of thrust after years of experiments. The Germans had made an engine 60 times more powerful, and they were making lots of them. Dr. Theodor von Karman, who was in charge of the Jet Propulsion Laboratory at Caltech, was one of the first American scientists to really look at the V-2. His team had been working on rocket technology for the Army since 1942. They were working on what would become the Corporal missile. When von Karman saw the V2's engine, he was blunt. We are at least 7 years behind. The engine alone had many new technologies. The combustion chamber had a double wall. Alcohol fuel flowed through the outer wall before going into the chamber. This cooled the chamber walls and heated up the fuel at the same time. This solved a major problem in rocketry. It kept the chamber from melting because of the extreme heat of burning fuel, which reached 5,100 degrees Fahrenheit. But the turbopump really shocked American engineers. At the center of every V2 was a steam-powered turbine. It spun at 4,000 revolutions per minute, powering pumps that forced fuel and liquid oxygen into the combustion chamber at 125 liters per second. The turbine made 600 horsepower. The pumps had to handle liquid oxygen at minus 297 degrees Fahrenheit, while operating at pressures that would destroy regular pumps. American engineers stared at this device with a mix of respect and frustration. The turbopump showed 7 years of German work. It included new metals, precise machining, and ways to solve problems that didn't exist in American industry. The turbine blades were made from nickel-chromium alloys that could handle extreme temperatures and forces. The pumps had seals that kept liquid oxygen from leaking while spinning so fast that any imbalance would cause a major failure. Lieutenant Commander Robert Truax, a Navy engineer who looked at the V2's engine, wrote in his report, "The German turbopump isn't just better than American technology. It's technology we don't have." Building one would require making new alloys, new ways of casting metal, new manufacturing methods. We think it would take at least 18 months to create a single working prototype, if we had unlimited money and access to materials that are hard to get because of post-war shortages. Then there was the guidance system. It showed how far behind America had fallen even more clearly. The V2 used a computer that used information from gyroscopes and accelerometers to control the rocket's flight. 2 gyroscopes, one for pitch and one for yaw and roll, constantly measured the rocket's position. An accelerometer measured acceleration and calculated velocity. When the rocket reached its programmed velocity, usually around 3,500 miles per hour, the guidance system turned off the engine. The sophistication of this system impressed American engineers. The gyroscopes were made with precision that American companies couldn't match. The computer processed many inputs in real time. It sent signals to 8 control surfaces, 4 fins on the tail, and 4 graphite veins in the rocket's exhaust stream. These veins were right in the rocket's exhaust at temperatures over 5,000 degrees. They were made of graphite that could handle the heat and provide steering during the first 60 seconds of flight. Dr. Charles Stark Draper of MIT, America's top expert in guidance systems, looked at the V2's controls with a lot of respect. Draper had spent years making gyroscopic instruments for airplanes and ships. When he saw the German system, he knew right away that they had come up with things his lab hadn't thought of. They solved the integration problem, Draper wrote. They made an accelerometer that calculates velocity by measuring acceleration. This is the first fully electronic control system ever used on any vehicle. It's like a fly-by-wire system, decades ahead of anything in aviation. But maybe nothing showed the gap in technology more than the quality of manufacturing. American engineers looking at V2 parts found machining that was more precise than regular peacetime standards. Welds were perfect. Measurements were accurate to thousandths of an inch. Parts that had a lot of stress were built stronger than they needed to be. American designers, who didn't have enough materials, would never have done that. An Army officer looking at the turbopump assembly wrote, "Every part seems designed to survive the worst possible conditions. The Germans built for reliability in combat. The fuel lines have extra backup systems that we would think are wasteful. The electrical system has more circuit breakers than it needs. The structure is heavier than it needs to be. This is engineering from a country that has the resources to build things right, not from a country struggling to build things cheaply." The electrical system alone was more advanced than what America was doing. The V2 used a 24-volt system with generators powered by the main turbopump and a separate turbine. American rockets, when they used electrical systems, used 12-volt designs with single generators. The V2's electrical system had 8 miles of wiring, all carefully organized and protected. The system included motor-driven valves, gyroscope power, ignition systems, and equipment that could send flight data in real time. When Robert Goddard looked at the V2 that May afternoon in Annapolis, he saw that it was similar to his own work in many ways. It used liquid oxygen and alcohol as fuel, turbine-driven pumps, gyroscopic stabilization, vanes for steering. In a letter to his supporter, Harry Guggenheim, Goddard wrote with some bitterness, "The Germans have used my ideas. They have taken what I developed and built it on a scale I could never achieve. The V2 is what my rockets could have been if anyone in America had listened." But Goddard, even with all his intelligence, didn't see the important difference that other American engineers saw right away. The Germans hadn't stolen American technology. They had created their own rocket program that, by 1945, was almost a decade ahead of what America could do. Hermann Oberth's theoretical work in Germany was similar to Goddard's. Wernher von Braun's team had started experimenting with liquid fuel rockets in 1932, using their own research. By 1934, their A-2 rocket had already gone higher than any of Goddard's rockets. The German program had money from the government, priority from the military, access to the best universities in Germany, and the work of thousands of scientists and engineers. Goddard's rockets reached their highest point, about 9,000 feet, in 1937. Later, the A-4 rockets often hit an altitude of 50 miles, high enough to be considered in space. They would then arc back down, aiming for targets around 200 miles away. Goddard's best rocket engine could push with a force of 985 pounds. In contrast, the V2 engine generated a massive 60,000 pounds of thrust. Goddard worked with just a few helpers in the New Mexico desert. He got his money from the Guggenheim Foundation, but the U.S. military didn't really pay attention to his efforts. Meanwhile, the Germans were working at Peenemünde, a huge base that gobbled up as much money as the American Manhattan Project, which developed the first nuclear weapons. It wasn't a simple matter of comparing American and German technology. On one side, you had a brilliant scientist, Goddard, working mostly on his own. On the other, you had an entire country's industries and scientists, all focused on building rockets for the military. By June 1945, American engineers were busy studying captured V2 rockets. Secret reports were going around inside the War Department. These reports all agreed the U.S. was in a risky spot. Rocket technology would be important in future wars. The Germans had shown that missiles could hit targets hundreds of miles away, and there was no way to stop them. Plus, the Soviet Union had taken over Peenemünde, the V2 factories, and snagged thousands of German rocket technicians. If the U.S. didn't act fast, they would be way behind in a key military area as the world moved forward. This thinking is what led to Operation Paperclip. It was a very debatable choice made right after the war. In September 1945, Wernher von Braun and 126 other German rocket scientists came to Fort Bliss, Texas, under the watch of the military. These were the guys who built Hitler's vengeance weapons. Some had even used forced labor from concentration camps. Their rockets had terrorized cities such as London and Antwerp. But they had knowledge that America desperately needed. The ethics of this decision bothered many Americans. These were, after all, scientists who had worked for the Nazis. Some even held ranks in the SS. They were responsible for weapons that killed thousands of civilians. The prisoners who built the V2S at Mittelbau-Dora suffered even more, dying from exhaustion in the underground factories in greater numbers than the rockets caused in the cities they attacked. At the time, the Cold War was just starting, and the Soviet Union was already putting together its own German rocket program, led by Helmut Grotrup and staffed with their of German engineers after they captured them. At White Sands Proving Ground, the U.S. military started putting together captured V2S for test launches. The first engine test happened on March 15, 1946. The first actual launch was on April 16. At 2:47 p.m., the German rocket, now rebuilt, took off from the New Mexico desert. Almost right away, the guidance system failed. A fin broke off. The rocket only reached about 3.4 miles high before crashing. It was a clear sign that even with German rockets and German scientists, America had a lot to figure out. Colonel Harold R. Turner, after watching that failed launch, told his staff, "We have the parts. We have the people who designed them. But we don't have the factories that built them, the experience to improve them, or the knowledge that comes from thousands of launches. The Germans had done that many tests and combat launches. We're starting from scratch." Over the next few years, They launched 67 captured V-2s from White Sands. Some worked well, others didn't. About 68% were considered successes, but that's still a high failure rate for combat. Each launch taught American engineers something new about rocket engines, guidance, how rockets fly at high altitudes, and the engineering problems of building missiles. Scientists from universities, military labs, and new aerospace companies sent their experiments up on the V-2s. They used instruments to measure cosmic radiation, cameras to take pictures of Earth from space, and sensors to study the upper atmosphere. On October 24, 1946, a V-2 carried a 35mm camera up to 65 miles high. It took the first photos of Earth from space. The images were grainy and in black and white, but they showed the curvature of the planet. It was a major moment. It showed what German technology had made possible, sending things beyond Earth's atmosphere and getting useful data back. But using captured German rockets was only a temporary solution. It was a way to learn how to build American rockets. In 1948, the Army Ordnance Department picked Redstone Arsenal in Huntsville, Alabama, to be the main rocket research center. Wernher von Braun and his team moved there, along with American engineers. They started designing missiles based on the V-2, but adapted to American needs and abilities. The first big American rocket from this collaboration was the Redstone. It was first tested in 1953. The Redstone used the V-2's design, liquid oxygen and alcohol fuel, pumps to deliver fuel, gyroscopes for guidance. But it also had improvements, like better fuel efficiency and more reliable guidance. American factories learned how to build rockets. By the mid-1950s, America was catching up. The Jupiter, Thor, and Atlas missiles were truly American rockets, built by American companies using American materials and techniques. When the Soviet Union launched Sputnik in October 1957, America responded with Explorer 1 in January 1958. The Saturn V moon rocket, which carried Americans to the moon in 1969, was designed by Wernher von Braun's team at NASA's Marshall Space Flight Center. Its F-1 engines each put out 1.5 million pounds of thrust, 25 times more powerful than the V-2. But the connection was there. Regenerative cooling, turbo pumps, gimbal-mounted engines to steer the rocket, and guidance. All of these things were tested in the V-2 and then improved to achieve what Goddard had dreamed of and what the Germans had made seem possible. Looking back now, the V-2's story is complicated. It was a weapon that didn't do much good in the war, but cost a lot of money and lives. The forced labor used to build it was a terrible act. But it was also the first practical missile, the first thing to reach space, and the thing that formed the basis for everything that came after in rocketry and space. For American scientists looking at those first captured V-2s in 1945, it was a wake-up call. The United States, with all its industry and smart people, was years behind a country it had just defeated. Robert Goddard's work had been ignored by his own government, while Germany spent a ton of money developing similar technology. The lesson was clear. To be the best in technology, you need to invest steadily, have a solid system of support, and recognize that one brilliant person can't do it all alone. It takes a national effort. When NASA named the Goddard Space Flight Center in May 1959, Administrator T. Heath Glennon recognized both Goddard and the uncomfortable lesson of his career. Goddard had dreamed of rockets that could reach the moon. He built rockets that reached 9,000 feet. The Germans, working on their own, built rockets that reached space. Today, the American space program builds on both of these things, but also on the idea that genius needs support, dreams need resources, and being a leader in technology requires a national commitment. In the end, the V-2 taught America three important things. First, that rocket technology would be important for military power and for getting into space. Second, that you could lose your lead in technology if you weren't careful, and you could only get it back with hard work. Third, that in the Cold War, the country that controlled space and had missiles that could reach far would have an advantage. The American scientists looking at that first captured V-2 in May 1945 saw all of this, even if they didn't say it out loud. They saw the distance between where America was and where it needed to be. They saw the cost of ignoring people like Goddard. They saw the future in German hardware, waiting to be understood, absorbed, and then surpassed. The warehouse in Annapolis where Robert Goddard examined the V-2 is gone now. But the rocket he saw that day and what it represented changed the course of American history. From that moment of realization, that understanding of how far behind America had fallen, came the determination to catch up, the money spent on rocket, and finally the success that would place American footprints on the moon just 24 years later. The V-2 was Germany's weapon. For America, it became something different, a wake-up call, a learning tool, and a challenge to do better. The fact that Americans eventually passed what the Germans had done, building rockets that carried humans beyond Earth orbit, showed that technological gaps can be closed. But you need to know the gap exists, commit the resources to close it, and understand that in technology, like in war, those who don't invest in the future will be left behind. When Wernher von Braun stood at Cape Canaveral in July 1969, watching Apollo 11 launch toward the moon on top of a Saturn V rocket, he looked back on the distance from Peenemünde to the Sea of Tranquility. "We always knew it was possible," he said. The physics were clear even in the 1930s. What changed was not the science, but the commitment. America in 1969 could do what Germany in 1945 could not. Focus the resources and the will of a whole country on reaching beyond Earth, not as a weapon, but as a success of the human spirit. That commitment started in a warehouse where American engineers looked at captured German rockets and faced an uncomfortable truth: they were years behind. The question was whether they would have the determination to catch up.